Hello, Jello. Concavity. Concavity. So, we want to talk about curvature of our functions, or the graphs rather. So we're going to distinguish two types of curvature. We're going to have what's called a concave up and a concave down. So concave up is, the cup. If this is a cup, the cup is facing up. And concave down, if this is a cup, the cup is facing down. So this one I would say concave up, and this here is concave down. Okay, these concavities can be more subtle than this. You can have something like this right here. This little guy is concave up. And concave down, you could have something like just subtly concaving down. So it doesn't have to be so explicit, the concavity. But roughly speaking, concave up means the cup faces up, and concave down means the cup faces down. Short forms, I will go CD. I'll say CD for concave down, and I will say CU for concave up. Now the actual definitions are a bit more subtle. So concave down, if you notice for concave down, if I think of a tangent, say here, imagine on my curve here, I have a tangent, you'll notice that the curve itself, the blue, is below the red here. That is the more formal definition of concave down. And likewise for concave up, if I have a little point here and I draw a tangent, you'll notice that the curve, the blue curve, the function f, is entirely above that tangent. Okay. How can we find concavity? Well, we're going to use actually the second derivative. So I will just give the statement of this test, and then I will talk about why this test makes sense. So the test is, well, if, if f double prime of x is bigger than 0 on an interval, then f, the original function f, is concave up on I. 2, the other way around. If f double prime of x is less than 0 on I, then f is concave down on I. Okay, so the second derivative determines the concavity. Why does this make sense? Well, let's look at this here. If f double prime is positive, now why does that correspond to concave up? Well, imagine you have something concave up, and you move from left to right. So if I were to draw a tangent here, if I drew a tangent here, and I were to draw a tangent at A, well, it's not very good, but you get the idea. Notice that the slopes are increasing. So let's say slopes increase from left to right. So what does that tell me? The slopes increase. So if I have a concave up chunk of my function, and this, I can see the slopes are increasing as I go from left to right. This one's about 0, and this one is, I don't know, 2/3 or something. What does that mean? It means that f prime is increasing. So maybe we'll put a logical connector here. F prime is increasing, therefore the derivative of f prime is bigger than 0. So this is just to help you make sense of this. So one more time, if you have concave up, then the slopes increase as you go from left to right. So f prime is increasing. So the derivative of f prime is bigger than 0. So f double prime is bigger than 0. Okay, that's how I make sense of it. Hopefully that's helpful. Inflection point. What is an inflection point? Well, an inflection point is a place where your concavity changes. It's kind of like a critical number, but in the land of the second derivative rather than the first derivative. So a critical number is somewhere where your function goes from, don't draw this. A critical number is where your function is temporarily horizontal, but it could mean that your function is going from decreasing to increasing. So it's switching from decreasing to increasing. Now inflection point is going to be where you switch from concave down. So let's say concave down to concave up. You see, it's hard to really say. I'll zoom in here. I think you can see here I have concave down. Over here I have concave up. But where does it switch? It's kind of subtle. I would say about here, There's a switch from concave down to concave up. We call this an inflection point. Could go the other way too. You could have a function going from, say, concave up, down. Oh, that's a bit chunky, but let's try to do that smoother. Let's go. Nope, still not good. I mean, it's hard to get this. I just want to drink less coffee. Oh, I'm not going to beat that. Let's say about there. This is my function f. So here you have concave up. You see the cup is facing up. And then you have concave down. So an inflection point. So the definition here, more formally, is concavity changes and f is continuous. We're going to insist that f be continuous here to rule out any situations that are too strange. Okay, that's an inflection point. So we're going to find these inflection points by just looking at where the second derivative changes. So concavity is determined by the second derivative, as we saw above. So we're going to look to see where f double prime changes sign. So my definition, concavity changes and f is continuous. We'll say at, say, C. Then this point C, comma, f of C. So an inflection point is an x and a y component. Different than a critical number where you're just taking the x there. But for inflection point, we have x and a y. So if we have this happening, then C, f of C is called an inflection point. And short form is IP. I'm missing a word here. Let's say the word right here. I'll put the word if. Concavity changes, and f is continuous at C. Then CF of C is called an inflection point. Okay, let's talk more rock. Let's do an example to illustrate. So we'll go back to this example here. Now I'm going to look at the second derivative and see what's happening. So f prime of x is 6x squared minus 18x plus 12. F double prime of x is 12x minus 18. So we're trying to figure out the sign of f double prime, so we should set it equal to 0. And then I get 12x is 18, x is 3 over 2. So my function is having no concavity there. So you can think of it that way. It's like an inflection point is where you momentarily have no concavity, meaning you are flat, you're a straight line for a microsecond there. No, not even a microsecond. Instantaneously flat. So I do a number line. I put my 3 over 2 there. And this is a number line for f double prime. And then I'll remind myself of what f double prime is. Nice and factored. We'll go 6. I'm coming from here. 6 x minus 3. No, 2x minus 3. You know what? I think it'll be more instructive if I factor out 12. 12x minus 3 over 2. Here's my f double prime. And I do test points into there. F double prime of, say, 0. 0 exists over here, so I'll use that one. It's always nice to use 0. And I get less than 0, right? Because I get 12 times a negative number. F double prime of, say, 2 is going to be bigger than 0. So my signs are a minus there and a plus there. So my concavity is changing at 3/2. And this function is continuous everywhere. So 3 over 2 is an inflection point. Okay, so from this diagram, we can answer our quiz. Diagram basically answers the question, right? It tells you that you have an inflection point. It tells you concavity. But we can put it into English and say concave up from 3 over 2 to infinity. Concave down on the other side, minus infinity to 3 over 2. And the inflection point. Well, the inflection point's a bit awkward here. I need to find C. Remember, it was C, f of C. I got my C value here, so now I need to find 3 over 2 f 3 over 2. So this is going to be tedious. I think I will just skip that calculation and just kind of cheat and look. But I want to make extremely clear that to find this y value here, I'm going to say it carefully, to find this y value here, I need to take my 3 over 2 and plug it back into my original function f, And what do I get? Let's take a quick sneak peek at the answer. My IPO turns out to be 3/2. That's a coincidence. Do not read into that carefully, or don't read into that conspiratorially. It is a coincidence that they're both 3/2. So again, to find this value here, I took 3/2, plugged it into my original function, given up here, did a annoying calculation, and found this value here.